So, Wien bridge is the Wien has nothing to do with Hewlett Packard. The Wien bridge is actually originally invented to measure the inductance and capacitance by using a bridge, Wheatstone bridge circuit, and in that context, Wien has given this method of measurement of inductance and capacitance using certain bridge configuration, and that is known as the Wien bridge, and same Wien bridge was used in making the oscillator, so it's called the Wien bridge oscillator. Okay, let's see what these oscillators are. Wien bridge oscillator basically is like this. You have an amplifier and then you have a resistor and capacitor to ground, and feedback network is again a resistor and a capacitor. This is the output. This is R. Not necessarily they need not be same, but the common practice to make this same. So the circuit doesn't require them to be same, but okay. So now, how do you analyze this circuit? What is A in this case? A is A, and this A is assumed to be independent of frequency and a constant. So this A is no S there with some constant value independent of frequency. At least in the frequency range of your interest where the oscillator must operate. The feedback network corresponds to this and this, because V0 is applied here and this voltage tapped out to feed into the amplifier here. So beta comes out to be equal to, if you call this as Z2 and you call this as Z1, Z2 by Z1 plus Z2. Potential division. So A beta comes out to be equal to and that must be equal to 1 according to our theory, Barkhausen condition. So which tells you that AZ2 must be equal to Z1 plus Z2. What does this statement mean? It means this circuit will oscillate at a frequency which is satisfied by this condition. So let us substitute what is Z1 and Z2. Z1 is equal to R plus 1 by j omega c, and Z2 is equal to parallel combination of this and this, which is R into 1 by j omega c divided by R plus 1 by j omega c. Right? So AZ2 will be equal to A into so this circuit will now oscillate at that frequency where this is met. So now if you simplify this, what do you get? Or so wasting time, let me write down the simplified expression. Let's just go home and do the simple one. 1 minus omega square RC plus 3 minus A into J omega RC must be equal to 0. This reorganizing on both sides, bringing this on this side and simplifying this expression comes out to be a simple result like this. And this is a complex number, so this must be equal to 0 as well as this must be equal to 0, right. So, real part condition is 1 minus omega square RC must be equal to 0. Imaginary part condition is equal to A must be equal to 3. So, the first equation tells you what is the resonance or the oscillating frequency omega naught square is equal to 1 by RC. So, omega naught is equal to 1 by something wrong here. It should be square, I think, here somewhere. Dimensionally something wrong here. Just check at home, but this is correct. Otherwise, dimensionally something wrong here. Okay. So, omega naught must be equal to 1 by RC. So, this will oscillate at a frequency given by radian frequency given by 1 by RC. All right. Provided A is equal to 3. If A is less than 3, it is not going to oscillate. If A is more than 3, it will oscillate. But if A goes on increasing much more than 3, the oscillations will tend to become not purely sine wave, but more complicated waveform, although the periodic waveform. So, A must be close to 3. But to guarantee that it oscillates, people normally keep this slightly more than 3 to ensure that if there are some losses in the network, they are made up by the gain of this amplifier. So, slightly more than 3, but theoretically is equal to 3. So, you make this amplifier gain is equal to 3 and choose the values of resistance and capacitance to satisfy this condition, which is equivalent to F naught is equal to 1 by twice pi R. Now, you have two choices, R and C, and this oscillator usually is a variable oscillator, in this sense frequency you want it to vary, like oscillator you have in laboratory, you would like to change the frequency. So, how do you change the frequency? By changing either R or C. The normal practice, because C cannot be usually varied over a wide range. So, people make a C a fixed value, say 0.1 microfarad, and then go on changing resistance by changing a potentiometer. So, depending upon the range of the potentiometer for this given value of C, you have a range of frequencies. If you want still higher range of frequencies, then you change the capacitor and again use the same potentiometer to again get the frequencies in another band. So, this is what we normally do in your laboratory. One is a stepped frequency change, other is a continuous frequency change.